In sections 8 and 9 of Chapter 17, we're going to discuss free energy and equilibrium. One of the things that we will be looking at in these sections is how to express the equilibrium constant K in terms of the free energy change delta G. In section 7 of Chapter 17, we looked at how to calculate the free energy change for any set of conditions using this equation right here. Now, if we're at equilibrium, delta G equals 0. So we basically are removing this term right here, and then we're left with this. And then rearranged, we get this equation right here. Q has been replaced with K since we're talking about being at equilibrium. And at equilibrium, we have an equilibrium constant. Now, if we wanted to solve for the equilibrium constant, we could rearrange the equation. E raised to the negative delta G divided by RT. Remember that temperature has to be in Kelvin. The R value is the universal gas constant, that is in joules. K can be any equilibrium constant, KSP, Ka, Kb, and so on. And when we're talking about a standard molarity, we're talking about a 1 molar solution. So we've talked about, standard temperature, 25 degrees Celsius, standard pressure, 1 atmosphere, standard molarity is 1 molar. And finally, when we use these equations, we are talking about the lowest free energy being at equilibrium as opposed to a reaction going to completion. This table summarizes the relationship between the standard free energy change and the equilibrium constant. In the first example, we are looking at the standard free energy change equal to 0. This would mean equilibrium. And if you look at the equation, in order to get 0 for an answer, the natural log of the equilibrium constant has to be 0. And that's when K is equal to 1. When the standard free energy change is less than 0, meaning when it is negative, the equilibrium constant is greater than 1. When the delta G is negative, that means the reaction is spontaneous, and if it's spontaneous, then it produces product. So when we calculate the equilibrium constant, it's products over reactants. If we have a lot of product, we get an equilibrium constant that's greater than 1. A reaction that favors products is also referred to as exergonic. When the free energy change is greater than 0, or positive, this is a non-spontaneous reaction. We don't get a lot of product that is produced. This reaction favors reactants and is referred to as endergonic. As a result, the equilibrium constant is less than 1. Not a lot of product in the numerator, a lot of reactant in the denominator. Let's take a quick look at this generic reaction here, A as it converts to B. We've got two graphs. On the x-axis, we have the fraction of A that is reacted, and then on the y-axis, we have G, free energy. We're interested in the lowest free energy, that is the equilibrium point. And you can see that's where the arrows are pointing in the graphs. When delta G is negative, that's the spontaneous reaction where our equilibrium constant is greater than 1, you can see that a greater fraction of A has reacted compared to the non-spontaneous graph where delta G is greater than 0 and the equilibrium constant is less than 1. We have a lower fraction of A that has reacted. Now let's look at a couple of sample problems where we get to work with some of these equations that we've been discussing. Our free energy change is negative 33.3 kilojoules per mole of nitrogen consumed. Spontaneous, right? Because it's a negative delta G. We're at 25 degrees Celsius, standard temperature. And for each of the following mixtures of reactants and products, we're going to predict the direction in which the system will shift to reach equilibrium. So we're not at equilibrium. We're not talking about calculating an equilibrium constant here. We'll do a problem coming up where we get to work with that equation. So we're talking about this equation from section 7. We know the standard free energy change that's given right there in the problem as negative 33.3 kilojoules per mole. We can look up R. We know the temperature. We want to make sure we have that in Kelvin though. And then we're going to take the information and solve for Q and see which direction our reaction is going to shift. So we substitute in what we know so we can solve for the free energy change. I did change the R value into kilojoules to match the kilojoules of the standard free energy change. Remember, when you're calculating Q, it's the same way that we calculate K, but we do have to pay attention to those coefficients. Those are going to be our exponents. When I solve for delta G, I get 0. This means the system is at equilibrium. There is no shift. For letter B, our pressures are all standard pressures. We're in the standard state. And when I substitute in everything and solve, my delta G is equal to my standard delta G. This represents a spontaneous process where the free energy of the products is less than the free energy of the reactants. We're seeing a decrease in free energy. The system will shift right to produce more products, and therefore we'll end up with an equilibrium constant that is greater than 1, a product-favored reaction. And finally, for this section, let's take a look at a problem from your end of chapter questions, number 72. We have some standard free energies of formation and some standard enthalpies of formation for some substances listed there in the table. Those substances are in the balanced chemical equation here. And we're going to calculate a few different things. The standard entropy change at 298 Kelvin, the equilibrium constant at 298 Kelvin, and the equilibrium constant at 3000 Kelvin. Remember, if you change the temperature, that changes the value of the equilibrium constant. So first, to solve for the standard entropy change, we can use this equation. Since we have the information in the table, that will allow us to calculate the standard free energy change and the standard enthalpy change. To calculate the standard enthalpy change, we'll do the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. We get 591.1 kilojoules. And to calculate the standard free energy change, we will take the sum of the standard free energy change of formation of the products minus the sum of the standard free energies of formation of the reactants, and we get 495.4 kilojoules. The standard entropy change is 0.321 kilojoules per Kelvin. You could also write this as 321 joules per Kelvin. Now, to solve for the equilibrium constant at that same temperature, we can use this equation or rearranged this one so we can solve for the equilibrium constant. Again, remember, you want your energy units for your delta G and R to match, so either put them both in joules or kilojoules. We know the standard free energy change from up here in letter A, and then we just need to substitute in for R and T, and then solve for K. We get 1.47 times 10 to the negative 87th. This is very, very tiny, definitely less than 1, and that corresponds with the delta G being greater than 0, with being a positive value, not spontaneous, and very reactant favored. Now for letter C, we want the equilibrium constant at 3000 Kelvin. This will be a different answer than letter B. And our delta G is going to be different. We are told that the delta H and the delta S are not temperature dependent. So we can use the same values that we did for letter A with the delta H, and then we solve for delta S in letter A. So we can use those same values. We'll just swap out our temperature for 3000 Kelvin, and we will get for our delta G negative 372 kilojoules. Now the reaction is spontaneous. We have a negative delta G. Now we can solve for the new equilibrium constant with the new delta G and the new temperature. And K equals 3.00 times 10 to the 6th, a very large equilibrium constant, much greater than 1, because now we have a spontaneous process. A spontaneous process produces products. And finally, in section 9 of chapter 17, we're talking about free energy and work. If you remember, we defined free energy as the energy that was available to do work. So the maximum possible useful work is equal to delta G. However, the amount of work that's actually obtained is always less. There's always a waste of energy. That's the main idea of section 9.